Good day, everyone. We are the Group 3 and we are here to tackle about the damage stability of the ship. So, first let's talk about its definition. So, the study of damage stability of a surface ship comes of use when the ship's water hull is affected in a way that it allows water to flood in any compartment within the ship's hull. Since these changes of the stability parameters of the ship, the extent of which depends on the extent of damage and flooding. So next is let me answer the question, how do ships get damaged? So in this case, I have listed two factors. The first one is compounded operator errors and the second one is storms and hurricanes. So first, compounded operator errors, which includes improper maintenance over time, multiple improper procedures leading to collisions with ships, rocks, reefs, piers, etc. The second one is storms and hurricanes, which includes water on deck, physical damage to hull, communications, radar, propeller, etc. It is really important to know how ships get damaged because if we doesn't know, we are not only risking the environment but we are risking our lives too. It is important that ships are able to survive in any damage sustained during the adventures it carries on high seas. The first step towards complying with the damage stability is to understand what it is and what is required of us. So next, what happens to ship stability when it's damaged? If the ship's stability is damaged, the ships will founder or the ship is foundering. Foundering is basically taking on water to the point that where the vessel becomes unstable and begins to sink or capsize. In short, foundering means sinking. So foundering, the word founder comes from the Latin fundus, which means bottom or base. And when anything founders, it usually means it has hit rock bottom in some way. When a ship sinks to the bottom of the water, it is said to have sunk. Consequently, when the ship is foundering, the hull starts to fill with water and it floods to the point where weight and now greater than buoyancy and the ship sinks.
So, good day everyone. Today I'm going to tackle about what will happen to our ship's stability when it is damaged. So, we have two here. First, capsizing and the second is plunging. So, the first one is capsizing. So, capsizing occurs when a ship is at sea and leads to one side to the point where it is unable to straighten or restore its original position, resulting in the vessel tipping over in the water and posing a danger to both the crew and machinery on board. So, other information about capsizing, this occurs when our ship is overloaded with our cargo or we have an unbalance of our cargo, wherein if the port has greater weight rather than the starboard. So in order to prevent capsizing, we need to have balanced weight in our starboard and port side. Also, we must not overload our ship. And the second is plunging. Plunging is when the front of the vessel is damaged at the bow and flooding begins in the bow. It spreads from the right, the bow, and sinks. And it sinks until finally it plunges below the surface of the water. So, para madali nyo maintindihan, so if the bow of our vessel is damaged, so it is located in front of our vessel. For example, this is the vessel and here is the bridge. And the bow is located here sa baba ng forward part. So kapag na-damage yung pinakababa dito, dyan papasok yung tubig. Kapag pumasok naman na yung tubig, it will sink our vessel until it plunges. So, meaning ng plunges is kapag yung barko natin ay nasa bottom na ng ocean floor. And next one is approaches for damage stability. Floatable length and factor of subdivision. So, floatable length and factors of subdivision. Although this is an ancient technique, it is nevertheless worth discussing because it establishes the groundwork for understanding damage stability. In this approach, the number of subdivisions required is calculated by knowing the floatable length along the ship.
Floodable length and factor of subdivision. The floodable length of a compartment is the distance from the margin line to the bottom of the compartment if it is flooded. Let us demonstrate this constructing a ship. We have a ship and we need to put subdivisions, bulkheads, to it to divide the ship into compartments. Floodable length and factor of subdivision. We create one compartment in the midship by placing two bulkheads. Let us mark this bulkhead as A and B. Now we want to place another bulkhead of aft of midship. Again, this bulkhead needs to be at a location C such that if compartment AC is flooded, the ship will sink to a point where margin line is just submerged. Floodable. And with this same approach, we can decide the location of other bulkheads along the ship's length.
I will discuss the floodable length and factor subdivision. When calculating the floodable length, one thing that we need to keep in mind is that we need to flood the compartment to the full width of the ship even when we have or plan to have a certain centerline bulkhead. Floodable length curve. Length curve. Floodable length curve represents the maximum floodable length of the ship along the ship length. This curve is obtained by vertical plotting the floodable length along the ship length. Floodable length curve. This is because if the midship compartment is flooded, the ship will sink bodily with less trim. But as we move away from the midship, the flooded compartment will trim the vessel. This would make a smaller compartment to sink the ship up the margin line. Floodable length curve, checking the damage stability compliance. Floodable curve method. Ships that are required to comply with this method of damage stability would be provided with the floodable length curve. The damage stability rules for the ship would be something like: the ship should be able to survive the breach, flooding of any one, two, or three compartment. To check if the ship would comply with this damage stability requirement, the floodable length curve is superimposed on the ship plan. That's all. Thank you.
Then one compartment by one, the damage stability compliance is checked. The length of the assumed damage compartment is plotted vertically at the center of the compartment. If this length is below the floodable length curve, this compartment complies with the damage stability requirements of one compartment standard. Same is done with the other compartment. As we can see, at the length triangles are within the floodable length curve of the ship. This means that the ship complies with one compartment standards of the damage stability. Now let us check the damage stability compliance for two compartment standard. In this case, we will assume the flooding of two compartments and compare the length triangle with the floodable length curve of the ship. Again, same is done assuming flooding of any two adjacent. Clearly, this ship does not comply with damage stability requirements of two compartment standards. If we need to comply with two compartment standards, this ship needs to have more compartments, the length of which need to be such that even when two compartments are flooded, it will be below the floodable length curve. Maybe the below subdivision of the ship will be able to satisfy the damage stability requirements for two compartment standard. Let us check the damage stability compliance of two compartment standards, floodable length and factor of subdivision. As you can see, the ship is a two compartment standard ship now. We can go on in the similar way if we want to build a 3 compartment or 4 compartment ship. Remember, Titanic was a 4 compartment ship and so was called the unsinkable ship.
So now let's proceed to watertight integrity. So the watertight integrity is the vessel's hull must be tight to prevent water from entering the vessel. At the same time, closing devices to openings through which water can enter the vessel has to be in perfect order. This applies among other things to overboard and bottom valves, hatches, doors, windows, portholes, and vents. And watertight integrity is vessels are subdivided into compartments in order to minimize the effect of water flowing in the vessel and between watertight compartments. And watertight means that water or any other liquid is not able to pass through the structure into or out of any of the watertight compartments. In other words, watertight means prevention from the passage of water in any direction. The vessel's hull, main deck, and bulkheads between watertight compartments must be watertight. Watertight bulkheads must be watertight at least up to main deck. Any openings in such bulkheads must be equipped with watertight closing devices. And now, let's proceed to calculating transverse stability after bombardment has been damaged. And here we have a sample problem. A box-shaped vessel which is 55 meter long and a width of 12 meter wide floats in salt water on even keel at a draft of 4.3 meter, a centerline longitudinal waterline. Bulkhead extends from end to end, and for the full depth of the vessel, a compartment midship on starboard side is 17 meter long and contains cargo with permeability with denoted letter of U of 34%. Then calculate the list of if each compartment is kg is equals to 3.6 meter. So here the illustration of our problem. So the D1 is just the half of the total breadth, which is the 12 meter. So here the solution. So the first one is the bodily increase in draft, and the formula is volume of lost buoyancy over area of intact water plane. So 34 over 100, which is the 34%, which is the permeability, and the 17, which is the midship longitudinal, the 6, which is the half of the breadth, and the 4.3 over 55, which is the total length, and the 12, which is the total width, and 34 minus 34 over 100, which is the permeability, and 17 of times 6, and in calculating we've got 149.12 over 625.32, and the answer is 0.4 rather. And the new draft is we just plus the 0.24 to the 4.3, which is the central line longitudinal water height, and we got the 4.54 meter dito. So the next one is finding the BB1, and the formula is equals to permeability A times B over 4 over LB, or the length of the bridge, minus A. So here the substitution, 34 over 100 times 17 times 6 times 4.3 times 12 over 4.3 over 55 times 12 minus 34 over 100 times 17 times 6, and we've got 96.8 over 625.3, and BB1 is equals to 0.15 m or meter. And here to find the list and to find LOZ, we must find first the LCL, and the formula is LB cube over 3 minus permeability B cube over 3, and here the substitution, 55 times 12 cube over 12 minus 34 over 100 times 17 times 6 cube over 3, and we've got 7,120 minus 416.17, and with that the LCL is equals to 7,503.83 m4. So with that we can get now the LOZ, which is equals to LCL minus A times BB2 over 1, and substitute the ICL, which is the 7,503.8 minus 625.3, which is the LB minus A, times 0.15, which is the BB1 over 2, raised to the power of 2 rather, and we've got the LOZ is equals to 7,490 m. So for the next one is the BM2, which is equals to LOZ over B, and we substitute 7,490 over 55 times 12 times 4.3, and we got 2.64 meter. And for QB2 we have here D2 over 2, which is the 4.54 over 2 equals 27. Then BM2, in getting the KM2 we just add the BM2 and KM2, which is 2.64 plus 2.27 equals 4.9. and for GM2 we just need to subtract the KG for 2 KM2, which is 4.91 minus 3.6, and the GM2 is 1.31 meter. And for the last one, which is the tan list, which is equals to BB1 over GM, and the BB1 is 0.15 meter over 1.31, and we got 0.114. Since we need the angle, we just need to shift tan, and the list is the list is 6 angle 32 minutes. And here are the sources, and that's all for our reporting. Thank you.